Okay, so let's talk about an application of integration. So we're going to find the volumes of some three-dimensional figures. So because we're going to talk about several applications of integration, let me talk about something general real quick, which is just reminding everybody what is integration. And this is going to be a bit informal, maybe to make sure I don't say anything terribly wrong, let's assume that f is continuous on the interval a to b. For us, right now, this assumption is always going to be true. We're also going to eventually see some examples where we have to deal with discontinuous functions. But for now, let's assume that the function is continuous. So, of course, integration, the way it's introduced, is motivated by finding the area underneath a curve. So imagine that we have some curve, y equals f of x, and we have some interval from a to b. And the idea behind integration is that we're going to approximate the area, and then we're going to do something that makes this approximation better and better. And what that is we're going to draw a bunch of little rectangles. So I split this interval from a to b up. I choose some numbers in between. So a is going to be x0, and then there will be an x1, an x2, an x3, and then b will be x sub n, where n is some number that we get to choose. In the end, we're going to choose n to be very large, but n is just some number for right now. And then what we do is we use these numbers to break the interval up into smaller intervals, and in each sub-interval, that's what these smaller intervals are called, we're going to draw a little rectangle. And I didn't really draw the rectangles, but let me draw one. And of course, you know, if you remember how this is introduced, you have a choice of where to draw your rectangle. Like, I could use the left endpoint rule, and then that means that for each subinterval, so I'm looking at the first one here, for each subinterval I'm going to choose the height of my rectangle to be the left endpoint. So this is the left endpoint of my first interval, this would be the right endpoint. But if I'm choosing the left endpoint rule, then I would draw the height of my rectangle there. And then there, and yeah, this one is almost flat, so it hardly matters, but okay, so anyway, hopefully you get what we're doing. But of course, if we're going to use lots and lots of rectangles, in the end, it doesn't really matter whether we use the left endpoint or the right endpoint or the midpoint or whatever. Anyway, I don't want to get too off track here. The idea is, and again, this is whether you're using the left endpoint, right endpoint, or whatever, if you take the limit as the rectangles get skinnier, so I'm taking like closer and closer together points, that in other words that means like n is going to infinity, because I'm going to need more and more rectangles to cover from a to b. If the rectangles are going to be very skinny, I'm going to need a lot of them. And as the rectangles get skinnier, if I add up the areas of these rectangles, it gets closer and closer to the true area. So that this is like the shaded region is representing the true area. In terms of more formula-looking things, we have this line. This represents the sum of the areas of the rectangles. Of course, a rectangle is a convenient shape to use because the area is very easy. It's just height times width. And this is the height of the ith rectangle. There are n rectangles, so I'm going to sum from I equals 1 to n. And so you can think of I as like, when I is 1, we're talking about the first rectangle. When I is 2, we're talking about the second rectangle, and so on. The height of, say, the first rectangle, so imagine that I is 1. The height, well, the way I drew it here, I used the left endpoint. So it's like, it's f of x0. But of course, as I discussed, you can use the left endpoint, right endpoint, or whatever. So we just call that x sub I star. And an x sub I star could represent the left endpoint, the right endpoint, or whatever. So that's the height of a rectangle. And this is the width of a rectangle. This delta x sub I, that just represents like this x value minus that x value. So that's the width of the appropriate rectangle. So I'm adding up a bunch of areas of rectangles. So I do height times width for each one. I add them all up. That's what this means. And as we discussed, as n goes to infinity, or the rectangles get skinnier and skinnier, this represents the true area, which we write this way. This is the indefinite integral, and of course we learned in Calc 1 that the way you find this, or the standard way to find this, once you know the fundamental theorem of calculus, is to find the antiderivative and plug in b and plug in a and subtract. But let me not get ahead of myself here. Okay. So the reason why I just went over this is this doesn't necessarily have to have anything to do with area. This could just be like any sum that looks like this that we set up, and assuming that we have some numbers x sub I that are getting closer and closer together, this goes to this. So we are going to use that concept to now find volumes instead of areas. So let's find a volume of something, or I'm going to show you how to use this idea to come up with a formula for a volume. So first of all, what are we doing? Imagine that we have some graph, y equals f of x, from a to b again, and I'm still assuming that f is continuous. That's true for all of today. And what is this thing? This indicates that I'm going to spin, or I'm going to revolve this shape around this line. So I am not a great three-dimensional artist, so bear with me, but imagine like spinning it around this. And so this, it makes a three-dimensional shape. Maybe I should have drawn that lower. It makes a three-dimensional shape, and we're going to find the volume of that shape. Okay, so what do? We break it into a bunch of small pieces. I'm going to find or approximate the volume of each piece. I'm going to add them all up, and then I'm going to take the limit as these pieces get skinnier and skinnier. So here we go. Again, I choose some numbers, x0 through xn. x0 is just a, xn is just b, and then the rest of the x's are somewhere in between. And I imagine cutting my region up according to these numbers. And if I do the same thing that I did for area, like maybe I draw a rectangle whose height, and it doesn't matter if I use the left endpoint or right endpoint because I'm going to take the limit. But I choose a rectangle for each one, and I spin that rectangle around this line. It's going to make what we call a cylinder, right? Here I drew a picture of a cylinder. And let me just remind you real quick, the volume of a cylinder is pi r squared h, where r is the radius and h is the height. Keep in mind that, of course, in this picture, we're imagining taking these numbers x very close together. So the height of the cylinder is going to be very short. These are very short cylinders. Also, they're sideways, so maybe it helps to turn the picture this way. But so they're sideways, and the height is very small, but they are just cylinders. So what do? I add up the volumes of the cylinders. So here I have the formula for the volume of a cylinder. So I go pi, and then what's the radius of the cylinder? Of course, these cylinders are sideways, so the radius is like from here to here. In other words, that's like f of x. So I wrote f of x sub I star, and again, the x sub I star could be the left endpoint or the right endpoint or whatever. So that's pi r squared, that's my r. And then what is h? H is the width of the interval, and that's what we call delta x sub I. Okay? Now we imagine taking these slices skinnier and skinnier, And the same way this goes to this, you know, what is the difference between what I have up here and what I have down here? Well, there's a pi, this one is squared, and other than that, there's not really a difference. So I carry the pi over. Instead of doing f of x, I do f of x squared, and so it turns into this. All right, so that's the formula I was trying to derive for you. Of course, we can use the same method sort of sideways, so to speak. So if instead of having y as a function of x, I have x as a function of y, and then y goes from a to b, and then I drew this revolving thing here, so we're spinning it around the y-axis, so it's going to go like this. Then, you know, I won't show all the work again, but basically you just switch some things around. I'm going to integrate with respect to y, so there's a dy instead of a dx, and it's whatever this function is squared, and I integrate from a to b. So in general, regardless of whether you're doing it regardless of whether you're doing it the first way I showed you or the second way I showed you, this is what I remember. Basically, I just remember it's the integral of pi r squared. And of course, there's some blanks to be filled in, and that's what I wrote around here. You have to figure out what the appropriate limits of integration are, and that depends whether you're integrating with respect to x or y. These are going to be x values or y values. This r, it's the radius of a slice, and then when I say slice, I mean like a very skinny, it's like these things, but we're imagining them getting skinnier and skinnier. So I imagine it like I'm slicing through the shape with my hand. And so in this first example, the r was f of x, because if I'm slicing it like this, the radius is this distance, and that's f of x. If I'm doing it this way, my r, like my slice, is going horizontal, and so my r is this, and that's g of y. But whatever it is, this is the radius of a slice. And then you're going to need to fill this in with either dx or dy, and that's whichever variable you're changing to get different slices. Like here, I put a dy, and that's because I'm changing y to get different slices. Like I could take my slice here, or I could take my slice lower, and what I'm doing is I'm changing the y value when I move my hand up or down. So yeah. Okay. So now that we know the disk method, the washer method is going to be pretty easy, actually. The washer method you could describe as just doing the disk method twice. So imagine that we have a region, and now there's a function that's bounding the region on the top, and a different function that's bounding the region on the bottom, and x is going from a to b. And I drew the revolving thing here, so we're imagining like spinning it around the x-axis. And so this shape, if you can visualize it, it has a hole in it, like I could stick my finger all the way through this three-dimensional shape, because it's going to go like that, instead of being like solid, like the first examples that we did. But basically, one way of looking at this is I can act as if the shape is solid and find the volume of what that would be. And then I can find the volume of like the hole and just subtract, like take the volume as if it was solid and then subtract the volume in the middle that isn't really there. And that's all this formula is telling us. It's pi, like, if it was completely solid, I would just get this. And the volume of the hole is this. So I subtract them, and I get my answer. I can put this in a general form like this, similar to the way I did the disk method. And of course, there's always, let me start that sentence over. Of course, I could do this sideways. Like I could have x equals f of y and x equals g of x and draw like a sideways region, and then I would set up my integral and there would be like a f of y here and a g of y here, and this would be dy instead of dx. In general, what I remember is this form. So there's going to be some appropriate limits of integration, whether you're integrating with respect to x or y. These are x values or y values. Then I'm going to do pi times the big radius squared. The big radius is basically, it's the curve that's farther away from the axis of revolution. The axis of revolution is this line that we're spinning it around. So big R, at least in this picture, is f of x. That's the one that's farther away from this line. G of x is the little radius. That's the closer one. So I do pi times the big radius squared minus pi times the little radius squared. And then I have to fill this in with either dx or dy, and again, that's whichever variable you're changing to get different slices. So on the way that we set this up here, it was dx because I'm taking my slices this way, and how far to the left or to the right I move my hand is changing the variable x. That's why this is dx. Okay. Couple quick examples. Let's find the indicated volume. So notice the axis of revolution is here. We have, maybe I should shade this just to be clear what region we're doing. So I'm taking this shaded region and I'm revolving it around the y-axis, and this line is y equals 1 minus x. So this looks like this looks more like this way, especially because I'm revolving it around the y-axis, right? So, okay, first of all, when we set it up this way, I had x as a function of y, and I don't quite have that here. Of course, this is easy enough. I can just solve this for x. It was given to me solved for y, but I can rearrange it. So I solve it for x, I get x equals 1 minus y. And then I'm just using this formula, right? So it's integral, and these are y values because I'm going to integrate with respect to y. So my y values for the region that I'm looking at, it looks like the bottom is y equals 0 and the top is y equals 1. Okay, so I put my pi here, and I put my g of y squared. Here's g of y. That was the point of solving this for x, is so I could find my g of y dy. Okay, and typically for most people, assuming that you're good with all the skills you're supposed to have, typically this is the hard part, is setting it up. From here on out, this is, you could say, easy stuff, assuming that you remember how to do all of this. So let's go. Pi is just a constant. You can pull that out. In fact, these formulas that I showed you, I can point to any of them, but they all have a pi in there. When you're dealing with these, you can always just pull the pi out. It's no problem. Anyway, so we did that. Now, maybe let's do some more algebra, because I've got a 1 minus y squared here, so my life is going to be better if I just FOIL this out. So this is 1 minus 2y plus y squared. Okay. Now, I'm ready to do antiderivative. So let me keep my pi on the outside. Antiderivative of 1 with respect to y is just y. Antiderivative of 2y is y squared. Antiderivative of y squared is 1/3 y cubed. And I have to put in the numbers 0 and 1. Okay, let's... use plenty of parentheses here because the pi is going to distribute to everything, so I want to make sure I remember that. And then I'm going to plug in 1 for y, so 1 minus 1 plus a third, and then I'm going to subtract what I get from plugging in 0 for y, and I am delighted to see nothing but zeros when I plug in 0 for y. So, okay, and then these cancel, so in the end I just get pi times 1/3, so... yeah, so that's the volume. And yeah, by the way, what we just found is the volume of a cone, right? Visualize spinning this triangle around this, and you get a cone. If you remember, at some point, you probably learned the volume of a cone. Of course, we just kind of did this the hard way, but let's check our answer. The volume of a cone, if the base has a radius of r and the cone has a height of h, is, oh boy, hopefully I remember this, 1/3 pi r squared h. And the cone that we had, the radius, like if we spin this around, the radius would be this distance, so that would be a 1. And the height would be this distance, so that's also 1. So this formula is also telling us we should get pi over 3. So math really works. It didn't give us the wrong answer. Okay, anyway. Let's do another quick example. So this one is set up but do not evaluate. You want to pay attention to when the instructions say that, because you don't want to do more work than you have to. Also, some of these, if it says set up but do not evaluate, that could mean that evaluating it is a lot of work, and you may not want to bother with that. Anyway, we're going to set up an integral for the volume formed by revolving the region bounded by y equals 2 square root of x and y equals x around the line y equals -2. And I started to draw some axes here, but I decided to leave this question without drawing a picture. It may help you to draw a picture, but you may also receive questions where there isn't a picture drawn for you. On the last one, we had a picture drawn for you, and we sort of trusted the picture when we were coming up with the limits of integration and that type of stuff. But you may not have that information. You may have to figure it out. So one other thing to notice about this one is that I'm revolving it around the line y equals -2. In the examples that we've done so far, and in the derivation that I showed you, we were always revolving it around either the x-axis or the y-axis. But now I'm revolving it around, well, it's a horizontal line, and that's always going to be the case for the examples that I give you, either horizontal or vertical. But it may not be the x-axis or the y-axis. It may be some different horizontal line or some different vertical line. So I just drew the axis of revolution. So I drew this little thingy that you always see around the axis of revolution. Let's try to draw the rest. This is one where we don't know where these two curves intersect. This is described as the region bounded by this curve and this curve. So let's find the intersection points. So I take this, set it equal to this, and let's solve. So let me square both sides. So I get 4x equals x squared. I don't want to divide by x because that could mean dividing by 0. And in fact, I can see that x equals 0 is going to be a solution, and I don't want to lose that. So instead of dividing by x, I'm going to subtract everything over to one side. And then factor it. This will be easy enough. So I get x equals 0 and 4. Those are solutions to the original equation, so I'm happy with that. And I can probably draw a picture. And again, the picture is not strictly necessary. It just may be helpful here. So let me go. I know my intersections are 0 and 4, so I counted up to 4 on the x-axis. And looking at these two curves, I do have some idea what they look like. This one's really easy. Y equals x is really easy. That just looks like this. Y equals 2 square root of x. Of course, square root of x looks like this sort of sideways parabola, or at least like the top half of it. The 2 just stretches it vertically, so it's going to be taller. And I know that it's going to cross here and also here, so that's probably a good enough picture. And again, the picture is not strictly necessary. The instructions don't say you have to draw a picture, but it can help. So this is the region bounded by these two curves. Okay, but the important part is setting up the integral. So let me pull up, or maybe these can sort of fit side by side here. This is going to look like the washer method because like here's my axis of revolution. This is not like a solid region. Like the region does not go all the way down to touch my axis of revolution. It's like farther away. So this is going to be a washer method. So here's how I set this up. First of all, let's decide what goes here. This is like dx or dy. It's whatever variable we're integrating with respect to. And the nice way to figure this out is which variable you're changing to get your slices. So I'm imagining my slice is like I'm drawing it this way, and then I'm revolving, like I'm making a shape with a hole in it by taking a vertical slice and revolving it around this axis. And what variable do I change? I can take my slice farther to the left or farther to the right, and that's changing the variable x. So this is going to be a dx. Leave myself plenty of space. This is probably too much space, but better safe than sorry. So I'll write a dx there. These are limits of integration, and these should be x values because we just chose this to be x. And so the x values are 0 and 4. Okay. Now I'm going to have a pi, and why don't I just pull the pi out automatically? So that's going to take care of this pi and this pi. So inside here, I'll just do big R squared minus little r squared. Okay. What's big R? Big R is the curve, or it's the distance from the farther curve to the axis of revolution. And this is one spot where we have to pay extra attention to the fact that the axis of revolution is not just the x-axis. It's this other horizontal line, y equals -2. And big R is the distance from that to the farther curve. So the farther curve, this one is y equals 2 square root of x. So I want to do the distance from that down to -2. This is a little bit awkward, but... So I'm subtracting two y values. It's the y value of this curve minus the y value of the axis of revolution. So I end up doing minus -2. Okay. Now I have to go minus little r squared. Of course, this pi is taken care of. That's here. So I just need to put in little r squared. And okay, so I do the closer curve. That's this one. That's y equals x minus -2 again. And now is a good time to remember this said set up but do not evaluate. Of course, this is not impossible, and maybe I shouldn't be afraid of it, but you know, I'm happy to skip the algebra of this because I would of course make this a +2, make this a +2, but then I would have to FOIL this out and FOIL this out, and so, but we don't have to do that. This was just set up but do not evaluate. So I am happy to leave it exactly like this. Okay.